Okay, so this is a recording for Monday, 3/18, and it's going to be the conclusion of 6/4, possibly the beginning of 6/5. We'll kind of see how things go. I've mapped out with the class just now the schedule, tentative schedule. So we're planning on finishing 6/4 today. Possibly starting 6/5, working on 6/5 Tuesday, Wednesday, and Thursday if needed, with a review day being Thursday, partially or all day, and then Friday a review day. The exam part 1 will be on Monday, 3/25. I don't have the calendar in front of me. Is that right? The 25th? And then the homework will be due Tuesday, 3/26, and the second part of the exam will be then. The help session or the optional extra class will be Friday at 7:30 to 8:15. Possibly also like a Thursday after school option as well. So right now we're going to kind of see if we can get done with the notes for section 6/4. We talked last time, and I don't know if where exactly this is, but we talked about the projection here. It's probably on this slide. The projection of U onto V, and we've talked about several things. Oh, and here is that W2 is U minus W1, so we'll be having some work with that as well today. And we talked about the fact that this constant C that we need is like the dot product over that one vector, the magnitude squared. And oh, here's the actual slide that I wanted to see. So for the next couple problems, or the next problem for sure, we're going to use this. The projection of U onto V is U dot V over the magnitude of V squared multiplied times the vector V. And so that whole thing in parentheses is just a numerical value. Everybody agree with that? Because a dot product is a numerical value, a magnitude is a numerical value, and we square it. Yep. That is something that you're going to want to remember, and I will try in like maybe that review time and to kind of give you some pointers on things you're going to want to know for the exam. But since I haven't written it yet, I'm not there yet. So if I'm reminded, I'll say it that way also. If I'm reminded on maybe Thursday or Wednesday or Thursday, I'm reminded, then on Friday I will tell you some, bottom line. Here are the things that you need to know, because there are quite a few of them. But this one we certainly need to know for right now, today's problem, or a couple problems that we're going to do. So the projection of U onto V is U dot V over the magnitude of V squared times V as we... It is still a vector, yes. So this answer is still a vector, because that whole thing in parentheses is a numerical value, but then you're multiplying it times the vector, and the vector is either going to be in component form or linear combination form. So component form with the little greater than or less than signs and kind of an ordered pair type thing, or linear combination, something I plus something J form that we can look at this. So first we just start with, here's two vectors, and we're going to find the projection of U onto V. So this is number 5, vector U, and we're given these in component form, 3, -5, and vector V is 6, 2. And so this is just a pure math question. You know, no problem attached. It's just find the projection of u onto v, and then write u as the sum of orthogonal vectors, one of which is the projection of u onto v. And so that's just going to be like some extra stuff. So the first thing we want is the projection of u onto v. Oh, that's what okay, I knew I had written something wrong there. So the projection of u onto v, and with all those little vectory arrows things. And so just from that previous slide, the definition, or the way that we find that, is u dot v over the magnitude of v squared. I don't know, oops, my lines are a little wavy right now. And then times v, that vector v. So before I even do this, I'm just going to figure out those numerical parts. So u dot v is, how am I going to get u dot v? What times what plus what? Yes, so the dot product, 3 times 6 plus 2 times -5, or -5 times 2. So 18 minus 10. So u dot v is just the plain old number 8. And then we want the magnitude of v squared. So, you know, we're square rooting, but then we're going to square. So I'll find the magnitude of v squared is the square root of, and then we're going to square it. I'll just write it like that just to kind of remind us that if we have to find the magnitude, it is with the square root. And then how am I going to figure that out? 6 squared. Yep. 6 squared plus 2 squared. And so square root of 36 plus 4, but then we're going to square it. So square root of 40, but then squared. So it's going to be 40. And again, I just am putting the square rooting and the squaring because I know earlier in the chapter we'll have to find just plain old the magnitude. So now I'm just going to plug things in. So u dot v is 8. The magnitude of v squared is 40. And then I'm going to multiply, I'll put that in parentheses, and then I'm going to multiply that times the 6. 2 vector, and so that's like 1/5. Am I right? Just give, yes, that's 1/5 times 6, kind of 2, and then that is 6/5 and 2/5. So there is the projection of u onto v. And I think I have it all kind of written in there. And that's that part of the answer for this problem is, and I'm just going to go back up a little bit so that I can see this. So it said find the projection of u onto v. So that's that part of the answer. And then it says, then write u as the sum of 2 orthogonal vectors. So remember, orthogonal vectors are what? Perpendicular to each other, and their dot product is? 0. Their dot product is 0, and one of which is the projection of v onto u. So if we think here in this one, and I can't see everything as I go through this, but I need kind of my space down here. So that means that there are 2 vectors, w1 plus w2, that equal vector u. And the other one that I'm going to want is w2. So do you agree w2 is u minus w1, correct? w2 would be u minus w1. Do you agree? And let's just call, it says where one of these vectors, w1 or w2, one of them is the projection of u onto v. So I'll just call that W1. And U we also know. So we want this second vector. This is going to be our projection vector, is going to be W1. W2 is what we are going to figure out. And U we also know. Do you agree with that? So let W1 be the projection of U onto V, which was 6/5, 2/5. Thank you. 6/5, 2/5. And yes, and U we know from the very beginning. What is U from up there? 3, -5. And so if we just take that 3, -5 and we subtract the 6/5 and 2/5, then that'll give us W1. So we can write, we can write these two vectors that add to be U as we look at that. And so really I'm just going to get a common denominator. These are over 1 right now, so if I put them over 5, 15/5 and -25/5 minus 6/5, 2/5. So W2, which is our second vector that we need, is going to be what? What's 9/5? And -27/5. -27/5. So just subtracting those two as we go. So, well, let's just kind of make sure. So then it says, write U as the sum of two orthogonal vectors. So we know one of which is the projection of U onto V. So we have to write it as, we're going to write U, which is this one, is equal to that projection one plus W2. Do you agree? So we know that W1 plus W2 is equal to U. So I have to write it as a sum. And so that means that U is equal to W1 plus W2. So I'm going to go U is equal to W1 plus W2. And it's hard for me to be able to kind of quite see everything. So W1 is the 6/5, 2/5, right? And W2 I just figured out is the 9/5, -27/5. So W1, which is 6/5, 2/5, right? Correct me if I'm wrong because I can't see it. Plus W2, which is 9/5, -27/5. So that's the U written as the sum of these two orthogonal vectors. So can we check our answer? How can we check our answer? Okay, so yes, one check is if we add these two fractions, we should get that original U vector, right? So my two ways to check is to add these and see if they're U, and see if they are the original U. And let's just do that real quick. 6/5, 9/5 is what? 15/5. That's 3. And so we get 3. And 2 minus 27 is -25/5, which is -5, correct? And the other dynamic to check is that these are orthogonal vectors, right? So how can I check that they are orthogonal? That W1 and W1 and W2 are orthogonal. And I can check the dot product to see if it's equal to 0, correct? And so let's just do that. So 6/5 times 9/5 plus 2/5 times -27/5. And what's 6 times 9? 54 over 25 plus, and this will be negative 54 over 25, and so that's 0. Okay, so this ending part is just, you know, a way for me to check my answer, because really I should know these two things. I should know that these two add to be U, the original U, and I should also know that they are orthogonal, and I can check that as I go as well. Okay, so then we move on to some problems as we go. So this is another one of these little, you know, kind of like that boat problem that we had looked at last week. It's a 200-pound cart sits on a ramp inclined at 30 degrees, as shown in the figure. What force is required to keep the cart from rolling down the hill is kind of what's happening. And I like to draw it kind of without the cart just so that it's a little easier for me to see. We've got these things happening. So we have this vector v that is kind of right here that we're kind of, I don't know, like pushing it up the hill so that it doesn't go down the hill, acting on it. And that is 30 degrees. And then we can kind of have this right triangle here. W1 is the vector that is kind of pushing it down, and then this straight down force is, my F did not look well drawn. Ooh. And this F is kind of that straight down force as we go. So to me, that force vector, if you kind of think of that on a coordinate axis, it's going straight down, and with 200 pounds, as we look at that, and we can think of that as the magnitude or the distance. And since it's straight down, and if I think of this as a linear combination, so do you remember that's like AI plus BJ, where I is the vector that shows the horizontal change, and J is the vector that shows the vertical change. And do you agree that if I want to kind of have my end point of my vector right down here, that I can kind of apply that to the point 0, negative 200. Oops. Let me write my negative a little better. 0, negative 200. Do you agree with that? That if I plotted that as a point, so to speak, it would be 0, negative 200. So that's like 0I minus 200J minus 200J. Oops, and I forgot the little vector on I. So that's the linear combination form of that force as we look at that. And that can be considered like two vectors added together are kind of W1 and W2. And so what we want to do is we also want to remember that we've looked at the way to kind of put this in terms of some trigonometry as well. Let me kind of go through this. And so that gives us our F. Oops. I'm going to write that is a version of F as we look at that. And so if I wanted to clean that up, it's like negative 200J in linear combination form. And so now what we want to get is the projection of F onto the unit vector V in the direction of the ramp. And I'm actually just going to write that out in words because we don't have everybody here. The projection of F onto the unit vector V in the direction of the ramp. kind of as we go through. And if V is a unit vector, what's its magnitude? If V is a unit vector, what's its magnitude? Its magnitude is 1. So since it's the unit vector V, we can say that the magnitude of V is equal to 1. And so that'll kind of help us as we go. And then we're going to look at the component forms of that vector. So since this, if I kind of look over here, so I just said that magnitude is going to be 1, correct? So that kind of makes it easy for myself. And if this is that 30-degree angle that's right there, do you agree that if I kind of think of my little right triangle right there, that this x part of that is the cosine of that 30 degrees? So cosine of 30 degrees is this little mark I put here over 1, correct? And the sine of 30 degrees would be the vertical change there over 1, correct? And so we've written things this way before, but this means that that vector V can be, I'm going to say it as 1 times the cosine of 30, but I'm just going to write cosine of 30, correct? And if I want to write it in its linear combination form, I need a little room there. I can say it's 1 times cosine 30 degrees I plus sine 30 degrees J. And so I can put that in its component form as well. And so I can write them, or I said component form. I have them in their linear combination form. If I want to put them in their component form, I can do that as well. That's really where I wanted to go with that. So here's F, and here's V, as I have those two there. And so if I want to write them, I wrote them in their linear combination form right now as I was just working through them. But if I want to put them in their component form, I can just put them in those greater than and less than signs without the I's and J's, correct? So well, you don't hear that in the headphones of the recording, but we just heard a very interesting noise from the boiler room, which actually, except for that like shooing sound, no, but now we're doing the takeoff sound that we've heard before. Okay, so sorry to distract you. That maybe seems weird on the headphones here because you didn't hear anything, but this would be, F would be -2 or 0, -200, correct? In component form. And then V, well, we'll just kind of figure it out. V would be cosine of 30. What is the cosine of 30? Square root of 3 over 2. And sine 30 then is 1/2. And so, yeah, I didn't kind of talk through that. Got a little distracted by the boiler room. And so there's our two vectors. Now I'm going to do it just like the previous problem. So I have two vectors, and I'm going to find the projection of F onto V. And so I'm going to maybe write it right here. The projection of F onto V is going to be the dot product, F dot V, over the magnitude of V squared. Why is that desirable to me? What's the magnitude of V? 1, and so and then times vector V. And so we have to find that dot product a minute, and the magnitude of V we already know is 1. And so really I'm just going to rewrite this, since the magnitude of V is 1 and the magnitude of V squared would also be 1. So this is really F dot V times vector v. And so I'll go to maybe a different color, and I'll just write up here because then I don't go so far down. F dot v is going to be what times what? Okay, and so 0 times the square root of 3 over 2 is 0. Negative 200 times 1/2, oops, which I need another parenthesis, is negative 100. And so that's just going to be negative 100 times that vector v. And vector v is going to be that cosine 30i plus sine 30j, and I can write it in. I'm gonna write it in. I can either do kind of that component form or the linear combination form, and maybe I'm gonna write it in a linear combination form, but using those cosine and sines that we've already figured out. So that's negative 100 times. I'll start with the component form, square root of 3 over 2, 1/2, and so then that's in the component form. If I want to change it to linear combination form, negative 100 times the square root of 3 over 2i plus 1/2 j. And that's a good thing. It just kind of reminds me of our next section as we go through. And so that is that projection of F onto V, which, you know, I think in the previous problem we called it W1. We called that W1. And so, you know, I can say that that is W1. And just kind of, if you reflect back to that other problem, that would be kind of the W1 thing that's happening. And then really the magnitude of that force comes from that negative 100 as we look at that. So the magnitude, and kind of think about that in component form. Remember, v is a unit vector, and so this is a unit vector, and then that negative 100 is what we're multiplying by it, so that's kind of the magnitude of force to keep, I think it was a cart from rolling down the hill. Is 100 pounds. Is 100 pounds of for the magnitude of that force. So so that's kind of two of the same type of problems. One using using kind of a problem attached to it. And now we want to talk about work. And I'm going to be very upfront with you on work anyway. And I'm going to tell you the problem we do about work is the only problem you're going to have to do on the exam, if I put one on there, related to work. And so I'll give you several versions of that, but right now today I tell you the one that we will do a problem for, and that would be the one that we would look at. So we will go through these slides a little bit as we go. So the work W done by a constant force acting along a line of motion of an object is given by W equals the magnitude of force times distance. So the magnitude of the force times the distance as we look at that. And force acts along a line of motion. So, you know, if we're pulling straight across, that's great, but kind of think about maybe the examples we have is like a big barn door where maybe there's it's on a rolling rolling system, and you're maybe pulling with a string, so it's making an angle as you kind of pull it across, or even as simple as like a wagon or a cart. And you know, a lot of times you're not going to bend way down and pull it straight like that. You're usually pulling, you know, at an angle as you go. And so this is really when the constant force is not directed along the line of motion, then this is kind of the situation that we have. And this is the one that we're going to use right here. So you have to be able to set up this picture, I'm telling you right now, or a picture kind of like that. To get from P to Q, so it's this P, and maybe I'll write in yellow a minute. It's from that P to that Q. So we're kind of moving that box, cart, door, whatever it happens to be, from P to Q. So that's our kind of distance that we have there. And you can see way at the bottom of this slide. And this is the version that we'll be using as we go. And so let me get rid of that yellow again. And so we have that angle theta, which is the angle at which, you know, we're pulling. So our string is along this F kind of thing, or up or down, whatever, wherever it happens to be. And this is the projection of F onto PQ. PQ being that straight distance that we want to go, and theta is just this angle right here as we look at that. And so if we want to figure out the work that we've done, there we go, the work, and we have, here are 3 versions of the work formula, but I'm going to tell you right now, I mean, you know, you might want to write down all 3 of them, but the version that we're going to use is work, and I'm going to read through all of them. Work is the projection of F onto PQ. That's the projection form times the magnitude of PQ. And then the version that we're going to use is the cosine theta times the force, magnitude of the force times the magnitude of PQ. And, you know, it's also then this just vector F times PQ. That's the dot product form of work. And so that is a dot product as we look at it. And I think I intentionally put some homework problems and review problems that are kind of like the one that we're going to do, this version right here, with the projection as cosine theta times the force. So let's see. Then here's the definition of work. The work W done by a constant force F at its point of application moves along the vector PQ is given by either of the following. And here's the projection form, the dot product form, and then here's that alternate form. It's form 3 that I'm telling you right now that you're going to have to know. And that's W equals. I guess I don't even have that on there, but I'll, excuse me, I'll write that as we look at it. So make sure that you're aware of that. And then here is our problem to close. And this is hard to kind of visually see, so I always like to just redraw it. To close a sliding barn door, a person pulls on a rope with a constant force of 50 pounds at a constant angle of 60 degrees. And we are to find the work done in moving the barn door 12 feet to its closed position. And so this is kind of a little hard to see, and I'll just, you know, so essentially it's this door right here that we want to physically move it from point P to point Q, and that is 12 feet from there to there. And this is the projection, and I don't know if I can even get that in there, of F onto PQ. And, you know, it is in the picture. So then the deal is we're pulling our forces coming down like that. This is a 60-degree angle. And, you know, we're walking along 12 feet, you know, not necessarily this exact 12 feet, because we're maybe starting over here and then going a little bit that way as we go. And the magnitude of our force is 50, because it told us that we're using 50 pounds of constant force. So 50 pounds of a constant force as we go. And so we're going to do this work problem as work is equal to, and we're really using that projection version, the projection of F onto PQ times the magnitude of PQ. But then this version that says that that's the cosine of theta plus the magnitude of that force times the magnitude of PQ. So really, and I know it's a lot, and there's a lot in this chapter anyway, and so that's why I'm telling you right now that if I give you a work problem, it's going to be kind of just exactly like this. So what's our angle theta? 60. So it's going to be the cosine of 60. What's the magnitude of F? 50 times 50. And what's the magnitude of PQ? It's just that length or distance that is 12. So yes, it seems like very complicated and a lot going on, but really it's going to be the cosine of the angle times the force times the distance, you know, as we go. What is the cosine of 60? I feel like that's a half, yeah. And, you know, just because they're easy to figure out, we'll do it. If it weren't 60, we would just use our calculator. Times 50 times 12. And so what is the work? 300. And it's 300 foot-pounds. Foot-pounds, 300 foot-pounds as we kind of look at that. And so there's a lot going on in these questions, and that's really one of the reasons that I kind of I'm just telling you that if I give you a work problem, it'll be this work problem. So yeah, and so to kind of know that makes it a little bit easier. So I really think I'm just going to end today by saying we're going to do the trigonometric form of a complex number. And this might seem complicated to you when we do it, but it's kind of a back to kind of more just plain old math, I guess, or trigonometry. I'm happy to do that. I know, but and even though we don't talk a lot about polar coordinates, that's what's kind of going to be what we're looking at here. And so we're going to look at the complex plane where we have a real component and a complex component instead of just an X and a Y. So we'll save that for tomorrow.